Okay, so your midterm is going to have like 5 questions, and one of them's multiple choice and the others are all free response. And the main topics that you have to be familiar with are L'Hopital's rule. I'll write these down. So L'Hopital's rule, integration by parts, how to use formulas like lowering powers. So we talked a little bit about this last time. So like lowering powers and double angle formula, and well, I guess the reduction formulas are the same as the lowering powers formula. Okay, so the other thing that you have to know how to do, which we haven't talked about yet, is fraction decomposition. And then you should know a little bit about exponential growth, which we covered in the first week of class. And the other thing that you should at least have seen before is computation of arc length, right? So we're going to do sort of a lightning review of these topics, and then a lot of them I've put accompanying problems, which we may or may not get to. And I strongly recommend that if you study more, you try these problems, because I think they may or may not help you tomorrow on your midterm. And a lot of them you can find on Paul's online math notes, which is where I get most of my problems. Okay, so let's begin from the beginning. So L'Hopital's rule, okay? We've talked a lot about L'Hopital's rule, so hopefully you guys will be fine on this one. The idea is if you have f of x over g of x and you're taking a limit, as x goes to a, then if both the numerator and the denominator go to plus or minus infinity, meaning this could go to plus infinity and this could go to minus infinity, or both could go to plus infinity, or both could go to minus infinity, or both go to 0, then you're allowed to take the derivative of both the numerator and the denominator, and compute the limit of this instead. Now, it's incredibly important that you remember that both the numerator and the denominator must go to plus or minus infinity or to 0, because a lot of the time professors or high school teachers will try and trick you by giving you some limit that they expect you to try and evaluate with L'Hopital's rule, but really L'Hopital's rule doesn't apply. So be very careful of this. Okay, so now let me see what else. Why don't we do this practice problem? So try and evaluate this limit using L'Hopital's rule. And that's a 4, just so you know. Okay, so when you get an answer, just put the answer in the chat, because we don't have abundant time today. Look on my worksheet if you can't read it too. It's just on the worksheet A part 2, so A2. The top is a sine pi x. Also, it sounds like, oh, Jackson, could you maybe mute yourself? It sounds like there's some sort of robot voice in the background. Thanks. Okay, so that's 4 out of 10. Yeah, no problem. So that's 4 of 10, 5 of 10. Can we get to 7? 7 of 10? One more? One more person?
Sorry, quick question. What does the A and then the UU to the right of the problem mean?
Oh, this is just saying on my worksheet. If you can't read it, then it's A part 2.
Oh, it's the problem number. All right, thank you.
Okay, well, we're going to go over it now because we have many other things to cover. All right, so we put in -4, we get -4 pi, sine of -4 pi, and sine of -4 pi is 0 because 4 pi is a multiple of 2 pi. So then we get 0 in the numerator, and in the denominator, we also clearly get 0. So let's take some derivatives. In the numerator, we get cosine pi x pi. In the denominator, we get 2x, lim x goes to -4, and that gives you, okay, so cosine of 2 pi, which is the same as -4 pi on the unit circle, is 1. So then you get pi over -8, or -8 over pi, -pi over 8. Okay, great. So if you couldn't do that one, then definitely study L'Hopital's rule because you should be able to whip that out very quickly. Okay, so next problem. Okay, so another feature that may or may not show up on your midterm is integration by parts. So let's talk about it because we haven't talked about it yet. If you have an integral over something of the form AB, well, okay, let me give you the general form first. If you have something that looks like u dv, then when you integrate it, it's the same as uv minus the integral of du v du, okay? And so why does this work? Well, let's see what it means. So if we're integrating something that looks like AB, and we transform this in this way, let's say that A is our dv and B is our u, okay? So then we end up with the integral A, so integral of A, B, minus the integral of A, B prime, okay? And so this is what you'd end up getting using integration by parts. And why does this work? Well, it's basically because of the product formula. Like one way to think of integration by parts is you're just essentially reversing the product formula for derivations. And so this gives you, if you take derivatives, A, B, so derivative of A times B, plus integral of A times derivative of B, so B prime, and then minus, so we're taking the derivative of this thing, but by fundamental theorem of calculus, that's just integral of A, B prime. These two cancel, you get back AB, which is what you wanted. Okay, so D, let's just say like AB prime equals. Okay, so let's do some practice problems. I want you, well, look on the worksheet. No one can read my handwriting anyway. So look on the worksheet. It's B parts 2, 3, and 4. Okay, so I want you to try these 3 problems, and number 4 is actually kind of hard. So let me put you in breakout rooms for a few minutes so that you can ask each other if you get stuck. Right, so for the first problem, the only thing you can reasonably do is take a derivative of cosine, because, so let me write the problem. So you have 4x cosine 2 minus 3x dx, okay? And you're integrating this thing. So if you integrate this thing, you notice an x here. And what's stopping you from doing the integral, right? Because if you have cosine 2 minus 3x, you know how to integrate that. But because there's an x outside that's not the derivative of something inside, this is the holdup. And so in order to fix this, we can, so it's u dv, right? So what's the integral of cosine 2 minus 3x? We need that first. Well, okay, this requires a u substitution. So let u equal 2 minus 3x, okay? The derivative of u is equal to minus 3. And so that means that the integral of this thing should be, if you're putting a u in here, it should look like sine of u divided by minus 3. And so then all you have to do is replace the u with 2 minus 3x. And that gives you sine 2 minus 3x over minus 3, okay? So that's what happens when you take the antiderivative of that. So then you end up with 4x sine 2 minus 3x over minus 3 minus integral. Okay, so now we're dealing with this term. We just take its derivative. We get 4. Oh, and we have a sign now. Sine 2 minus 3x dx. Okay, so that's great. Now we know how to integrate. Sorry, I forgot the minus 3 again. We know how to integrate this thing. It's just exactly the same as our previous integral, except now we have a sine instead of a cosine, and we have a different constant out front. And so I'm not going to go through the process of integrating this because you can do it, but I think it should look like, so you get a minus cosine from integrating the sine, you get another minus by pulling out the minus 3 inside of the sine, and then you have another minus from the 3 in the denominator, so that gives you 3 minuses plus a minus here, which gives you 4 minuses, and so that gives you a plus, and then you have, so 4 over, okay, 9 cosine 2 minus 3x, and then this part just stays the same. You get 4x sine 2 minus 3x over minus 3. Okay, so hopefully I didn't make a mistake, but that is the idea. Is everyone happy with this?
Yeah, that helped out. Thank you.
Cool. Okay, for the next one, this one's a trick. If you have ln x, then you see that you have, so I told you it's an integration by parts problem. So you're looking for something to integrate by parts, but there's no good candidate that immediately pops out at you. So what you can do is you can rewrite it as 1 times x, okay? And so then you can make your dv the 1 and your ln x the u. And then you end up with, okay, so you integrate the 1 and you get x, ln x. Oh, sorry, we don't have an integral anymore. And then minus integral of, so you have x and you're taking the derivative of ln x, so that gives you x over x, and that gives you x ln x minus x because you're just integrating 1. Okay, and of course you need your plus c's on all of these, which I always forget. Okay, so the third one is more difficult than either of the previous two. So did anyone get this one? Cool. Okay, so let me see. We have integral of 6 tan inverse of 8 over x dx. Okay, so let me see if I can explain the thought process. When you look at this integral, you're looking for something that you can do integration by parts on again, right? But you see that you don't really have a good candidate again. And so when there's no good candidate, my guess would be you want to integrate the 6, okay, as one of your terms, like your dv. So Audrey, do you agree with me? Cool. Okay, so then what are you going to get? You'll get 6. So okay, udv, you get a 6x tan inverse 8 over x, and then your second term should be, okay, so you subtract the integral of 6x, and then the derivative of tan inverse 8 over x is 1 plus 8 over x squared, and then you have to take the derivative of 8 over x, and that's minus, yeah, sure, you can pull it out too. And then you get minus 8 over x squared. Okay, so hopefully everyone's following. That gives you, so your first term, you can just leave it alone. And the second term, we still have to integrate this, and it becomes, let's pull out the 6 and the 8. So then you'll get a 48, and we'll pull out the minus sign too. So that gives us a plus 48, and we're trying to integrate x over 1 plus 8 over x squared. And then you also have these x's cancel, and you get 1 over x. So we can ignore that x, right? Okay, so hopefully this looks good to everyone. Oh, 8 squared, 8 over x squared. Okay, so now we're in much better shape than we were before. Why? Because this 8 over x looks, 8 over x squared looks pretty similar to this 1 over x, right? And in fact, can we, yeah, so then we can do 48 integral 1 over 1 plus 8 over x squared times 1 over x, and then I'm looking for a u substitution here. So what should my u sub be? Can you help me out, Audrey?
This is about the point that I kind of got stuck, but I think I changed it so that it was 8x over 64 plus x squared. Right.
So you changed it so it was 8x over 1?
8x over 64 plus x squared. I'm not really sure, like, I think I did some things algebraically different. Like I pulled out the 6 at the beginning, but yeah, that's what I got. And that was easier because you can just use like the ln. So then it would be 4 ln of 64 plus x squared, or the absolute value, right?
Right. Thank you. Thank you. So then, right, you can multiply top and bottom, thanks Audrey, by x squared. And then once you do that, you get x squared plus 64 because this goes away. And then you just have this x squared in the numerator, and you can cancel out with x, and then you get 48, or now this is a 6 again, so then you just have an 8 in the middle. And now, oops, now we're kind of in good shape, because the derivative of this thing is just 2x, and you can see that this is 4 times 2x. So then you get 6 times 4 ln 64 plus x squared. And then you end up, just put this together with this part, and you get 6x tan inverse 8 over x plus 24 ln 64 plus x squared. Okay, so this is what, and then plus c, of course. Is that what you got?
Yes, exactly. Except I had the 6 factored out, but yeah, that's basically it.
Cool. Okay. Great. Let's keep going. Let's keep going. Okay, so the next thing that's pretty important, or maybe pretty important for your midterm, is you got to know how to lower powers and use double angle formulas, okay? So I think these are pretty good examples. I guess, cosine 6, that's actually a little bit strenuous. But so maybe cosine to the 4th is better, because cosine 6 to the 6 is kind of annoying, and I don't think we have time for that. So why don't you try and evaluate this problem? All right, so we're a bit low on time here. So I guess we're going to start going over it, though I bet most people haven't finished yet. So, okay, what do? Here, you can rewrite this as cosine squared x times cosine squared x. And now you can apply the lowering powers formula. So that gives you 1 plus cosine 2x over 2, 1 plus cosine 2x over 2. And then, okay, this gives you 1 plus cosine 2x plus cosine squared 2x over 4. Okay, you can integrate this, you can integrate this. This one you don't know how to do yet. So you got to lower the power again. This gives you 1 plus cosine 2x plus 1 plus cosine 4x. Yeah, the 1 is the 1 not divided by 2. I don't think so, because, yeah, I don't think so. Oh yeah, these ones. You're right. Thanks. So then that's a 1 over 4. That's a 1 over 2. Yep, sorry about that. So then this gives you 1 plus cosine 4x over 8, okay? And so now you know how to integrate all of these. And basically, yeah, this part's straightforward. So I'm not going to go further there. So why don't you also try for a couple seconds the integral of cosine to the 5th x. Okay, so for this one, it's actually much easier, even though it's a higher power, because what you can do is you can break this into cosine squared x squared times cosine x dx. And then the first part you can turn into 1 minus sine squared x squared times cosine x dx. And then you expand this thing out, you get 1 minus 2 sine squared x plus sine to the 4th x all times cosine x. Okay, but now you know how to evaluate all of these because cosine is the derivative of sine, right? And so that means you can just use u substitution on all of the individual terms, and then you'll get the answer pretty easily. So I think for the sake of time, I'm not going to finish this one either. Okay, so let me see, because we're starting to run out of time. I think one thing that I want to say, I put a fraction decomposition problem on here that I grabbed from Paul's online math notes. And for this problem, like I guess the only thing that I have to say about fraction decomposition is you have to be able to choose the denominators properly. So for instance, in this case, you have something that looks like 4x squared minus 22x plus 7 over 2x plus 3, x minus 2 squared. And so in these types of fraction decomposition problems, generally what you want to do is break up the powers, and you want to do something where you look at the individual terms and then you include powers of terms like this. So then you'd have 2x plus 3, x minus 2, and x minus 2 squared. And something like that, once you do the fraction decomposition, should get you something that you can integrate. Okay, so do that problem on your own because it'll take too long and it's a little too messy for the limited space I have. Okay, so I want to say something quickly about exponential growth. Actually, exponential growth will probably take a backseat on your exam, but you should still understand the basic idea. So this is a riddle that comes from something called the 3-question IQ test, which is kind of stupid, but it basically encapsulates everything that you have to know about exponential growth. So the riddle is, a pond has lily pads growing in it. Lily pads grow exponentially. It takes 30 days for the lily pads to cover 1/4 of the lake, and 31 days for them to cover 1/2 of the lake. How long does it take for them to cover the whole lake? Okay, can I get an answer in the chat? Okay, I have 2 answers. Three. Okay, I'm still missing a lot of people. What happened to the other 6 people? Yeah, okay, that's right. It is 32. So there was no trick here. It's just you have to know that exponential growth, the point is not the absolute number, it's just the ratio. And then if you want to try the second question in the privacy of your own home, which deals with cow growth rates in my home state of Missouri, then you can, and that might help you too. Okay, so the other thing that you should at least have seen before is maybe computation of arc length. And I included one question, which we're not going to do, but again, you can find it on Paul's online math notes. And let me just give you some intuition behind arc length. So if you have some sort of arc like this or curve, then what the arc length does is you take the derivative of y with respect to x, and basically if you look very closely on the curve, I guess it's easier on a convex curve like that. You have something where you're taking, or wait, that's not quite what I want. If you're taking the derivative here, it's very close to just moving a little bit further along the line, okay? And so what this is giving you, it's giving you dy over dx, okay? So that's like the change in y. And then the change in x is just dx, right? And so then what you're doing here is you're computing 1 plus dy over dx squared, because you're holding the rate of change in the x constant and you're looking at the rate of change in y. And then you just integrate this over the bounds that you want, okay? And this can be a little bit tricky because sometimes when you're taking integrals under roots, they can get pretty messy. But this is the basic idea. Like, you're just using the Pythagorean theorem in a very small differential sense in order to compute arc length by treating the arc as a bunch of segments that are straight, that are joined along infinitesimally small intervals along the curve. Okay? So, okay, again, I can't recommend enough that you try the other practice problems that we didn't have time for today. But as promised, I want to leave a couple minutes for questions right now. But don't ask me to do a giant fraction decomposition problem right now, because I don't want to do that on the whiteboard. Okay, so thanks for coming and good luck on your midterm.